Hello everyone, this is Dr. Kashif from Engineering College. Today we will check the heat conduction equation. That is very much basic equation which can be derived from the Fourier law of heat conduction. We will check it into detail, and we will also derive the other conduction equation in other systems. So first of all, we will check that temperature and heat are very closely related to terms that we use in the heat transfer systems. Temperature is a scalar quantity which just give us the magnitude, and heat transfer is a vector quantity where we can check that we also define the magnitude and the direction of the heat transfer. Just like here, we can see that the temperature is only 50 degrees centigrade, which is only giving us the magnitude, where the heat transfer have the direction outward from a baked potato. Similarly, because heat transfer is a vector quantity, so if axis is changed, then the heat transfer will change their signs. For example, from there, the heat transfer is taking place as a positive x direction, so the heat transfer rate is the 500 watt. And similarly, if we reverse the direction in the negative axis, the sign of the heat transfer will be reversed. So because we are discussing the heat transfer conduction equation, so there are three basic systems of that can be defined for heat transfer conduction, that are the rectangular system, which is having the coordinate of x, y, z, and t, where t denote for the time. Similarly, for the cylindrical system, we have the radius phi and the z and the time parameter t. And for spherical system, we have the radius, angle theta phi 1 and the theta 2, and the time parameter 2. So when we talk about the heat transfer, there are two type of heat transfer mechanism which can be defined. One is the steady and the second one is the transient. In steady, it means that the temperature is constant for a given operation time. For example, here the heat is conducted from a wall, and the temperature across the wall is 15 degrees centigrade and the 7 degrees centigrade at the time 2 p.m. And at time 5 p.m., the temperature across the wall is same. So Q1 is equal to Q2. It means that the operation of heat transfer here is steady state with respect to time. But on the other hand, if the temperature between 2 p.m. and 5 p.m. is changed, like 15 and 7 and 12 and 5, it's meant that Q1 and the Q2, where Q1 and Q2 are the heat transfer rate, are not equal. It's mean that the system is not steady state. The temperature or the heat transfer is changed with respect to time. There is a one special case in which the time in which with the time but not the position, means the variation with respect to time but the not with respect to position. The temperature and medium change uniformly with time. Such heat transfer system are called the lumped system. So because we are considering the heat transfer equation, so heat transfer equation can be in 1 dimension, 2 dimension, and 3 dimension. In the most general case, heat transfer through a medium is the 3-dimensional. However, some problem can be classified as 2 or 1-dimensional depending upon the relative magnitudes of heat transfer rates in different directions and the level of accuracy desired. 1 dimension, if the temperature in the medium varies in one direction only, and thus heat is transferred in one direction, and the variation of temperature and thus heat transfer in other direction are negligible to 0. So for in this case, we will only consider the 1-dimensional heat transfer because most of the operations that are being conducted in the process industries are related to only 1-dimensional heat transfer. So now we are starting the equation of heat transfer conduction. Consider a heat transfer conduction through a plane wall, such as the wall of the house, the glass of the single pane window, or metal plate at the bottom of the pressing iron, the cast iron system pipe or the cylindrical nuclear fuel element, and electric resistance wire. the wall of the sphere container and spherical metal ball that is being quenched or tempered. The heat conduction in these and many other geometries can be approximated in the one dimension, since the conduction through these geometries is dominant in one direction and negligible in the other directions. Next, we will develop the one-dimensional heat conduction equation for rectangular system, for spherical system, and for cylindrical system. But firstly, we will consider the heat conduction equation for rectangular system. So for that, we are considering a plane wall having the total length L, and the heat transfer is occurring in the x direction. This is the x direction. The red lines, arrow lines are showing that the heat transfer is conducted in the x direction. To make the heat conduction equation or to prove the heat conduction equation, we are defining an element here. This pink element here are considering in which the heat generation can be possible. So we will consider this small element having the thickness of delta x. Until here, the thickness is at the start of the element, the thickness is x. This is delta x, and the at point, the whole thickness is x plus delta x. So for this, we will next consider the energy balance on this system. This is the same rectangular system that I showed you before. So for the heat balance, we will consider the rate of heat conduction at point x and minus the rate of heat conduction at x plus delta x plus the heat generation in this element, that is basically a very small part inside of the whole wall, is equal to rate of change of energy content in this element. So now we will simplify this whole equation. So we will say that the heat conduction rate at x minus heat conduction rate as x plus delta x plus the heat generation inside this element and the heat accumulated with respect to time. We will solve this equation and we will get here the same, the heat conduction rate at x, heat conduction rate as x plus delta x. We will simplify it. We will make the basic definition of the derivative, which is known as the ab initio method. We will take the limit as delta s approaches to 0 and delta t approaches to 0. We will finally get this equation, which is the basic one-dimensional equation for the heat conduction equation. So in this equation, we can see there are a rate of change of temperature with respect to time term. And basically, this is the second derivative, two derivative involves, in which the thermal conductivity term is involved. And similarly, the heat generation term is involved. The density of the system is involved here. So we can change this equation depending upon which parameter are being changed. For example, thermal conductivity sometimes is depend upon the temperature, so it will not be a constant. We will consider it as a variable. Similarly, sometimes the density of the material will be changed, so we will consider it as a variable. And with respect to time, if the density will change, we will consider it as a variable. So for the steady state system, where the temperature with respect to time is 0, so this equation will be reduced to like this. And similarly, if there is no heat generation, the heat generation term would be equal to 0, and the equation are reduced to like this. And for a most probably that the most of the system work like this, that the steady state system is considered and no heat generation term is considered. So this general heat conduction equation in a one direction or in a one dimension would be simplified to this equation, which is the second derivative of temperature with respect to distance. So the simplification of one-dimensional heat conduction equation in a plane wall for the case of a constant conductivity of steady conduction with no heat generation. Similar procedure we will repeat for the cylinder. So this is a cylinder having, we are consider a small element having thickness delta R. We will consider the same procedure as we did in the plane wall. We will consider a energy balance, rate of heat conduction at R minus rate of heat conduction at R plus del R plus rate of heat generation inside this small element is equal to rate of change of energy conducted or accumulated inside that element. We will repeat it. We will make the complete derivation of the derivative, and we will simplify it and will make in a cylindrical system. So in this equation, as we previously defined, the term considering are the thermal conductivity, heat generation term, and the density of that material from where the heat being conducted. So similarly, if we simplify it for our given variables, we will summarize this equation like this. So this would be a equation for a system which is steady state and no heat generation. So this equation will result into this one. Similar is the case for the sphere system. We will do the same procedure of energy balance, and we will finally get this equation, and we can change it into for steady state, for transient, and for steady state and no heat generation system. So for all the three system of rectangular system, spherical system, and cylindrical system, we have the generalized equation in which we will change the value of m, and we will define a equation of one-dimensional heat conduction for a given system. For example, if we put n is equal to 0, or in this equation, we will define the equation of heat conduction in the plane wall. If we put n is equal to 2, we will define the heat equation of one dimension for a cylinder. And if we put n is equal to 2, we will define the heat conduction equation for the sphere. So similarly, as we define the heat conduction equation for one dimension in the x direction, the same can be done in the three-dimensional equation. So the rate equation of heat conduction will be defined in x, y, and the z direction. And similarly, we will check the heat conduction equation for x plus delta x, y plus delta y, and z plus delta z. So in the previous equation, we checked that we have the only one dimension, that was x direction. So if we apply the heat balance for next two dimension, that is y and z, that two terms would be included into the heat conduction equation if we consider the heat conduction equation in three dimensions. So that equation would be like this one. So in this equation, we can see that we have the x dimension, we have the y dimension, we have the z dimensions. So having the other terms like density, the heat generation, and the thermal conductivity terms have the same. So in the previous, we have the only x direction, the heat generation terms, and the heat accumulation term. But in the three-dimensional equation, we have the two other heat dimensional heat transfer equation, and the remaining all terms are same. So this is the final term, final equation in which x, y, and the z dimensions are included, having the heat generation term and the density terms are also included here. So this equation is known as the Fourier-Biot equation. So for the steady state system, the three-dimensional equation would be reduced like this. For transient and the no heat generation term would be like this. And for steady state and no heat generation, the heat equation for the three-dimensional conduction will be summarized like this. So as we have seen that the heat conduction equation has one, two, or the three derivatives involved. So it's mean these are the differential equation. And if we want to solve these equation, we must solve these differential equation. And for differential equation solution, we know that we need to solve the differential equation by solving it two times, because this was the equation that we have seen before, in which the temperature changes with respect to direction that was in the x direction. So for its general solution would be like this. If we take the derivative of this term twice, we will get this equation. And to solve this equation, we must know that what is the value of C1 and C2, because C1 and C2 are constant. To solve these two constants, we must know that what are the boundary conditions. So in the heat conduction equation, we have these five kind of boundary conditions that can be used to solve the one dimension or three dimension equation. So first one is the specified temperature at the boundary condition. Second is the specified heat flux boundary condition. Then is the convection boundary condition, radiation boundary condition, interface boundary condition, and the generalized boundary condition. So these are the very important boundary condition if we want to solve any system of one dimension heat conduction or three dimension heat conduction equation. So we will summarize it into a second derivative equation, and we will put one, two, or three, or any suitable boundary condition from these all to that equation, and we will solve it, and we will define the expression which will give us the temperature. So thank you so much. It was only for today.